In this video, we're going to be reviewing VSEPR theory. VSEPR theory is a way to take a Lewis structure of a molecule or a polyatomic ion, for example, and to visualize what it would look like in a three-dimensional way. Because molecules are actually 3D, they're three-dimensional. And that plays a big role in their structure, how they interact with things biologically, chemically speaking. So they actually do have 3D geometries. And so from the way you draw the Lewis structure, you can actually get what the shape of a molecule is going to be in a three-dimensional point of view. And to figure out the 3D shape, we have a theory called VSEPR theory. VSEPR theory. And so VSEPR actually stands for something. VSEPR stands for valence shell electron pair repulsion. And the idea is that it's the repelling of the valence electrons in your molecule that will lead to the overall 3D shape of your molecule. Because the electrons have the same charge, they're all negative, they're going to repel each other. And they're going to repel each other and space out in a way that minimizes the repulsion. They don't want to feel too strained. So they're going to space out in a way that minimizes the overall repulsion felt by the atoms and the electrons of that molecule. So when we're looking at VSEPR theory, there's two main factors that we need to look at to determine what the overall shape is going to be. There's going to be the number of peripheral atoms, so the number of atoms that surround a central atom, so number of peripheral atoms. And there'll also be the number of lone pairs of electrons on the central atom specifically. And so using your knowledge of the number of peripheral atoms and the number of lone pairs of electrons in a central atom, you can figure out what the shape, the 3D shape of your molecule is going to be. And then you can actually draw it out in a 3D shape. So we have a few images and tables here that show us what a 3D shape might look like. And you'll notice there's some slightly different notations or slightly different ways to draw a molecule in its 3D representation. So let's look at the example of CH4. So this is CH4 over here, and I'll show you how to use a table to figure out shape in a second. But CH4, if you were to draw a regular Lewis dot structure or Lewis structure, it would look like this. We don't have any 3D representation there. We're drawing it 2D on the plane of paper. But in reality, this is actually a three-dimensional structure. And the shape of this molecule here is this over here, which is the tetrahedral shape. And so to draw this in a more 3D representation, we use what's called a wedge-dashed representation, which means that we're not just going to use these solid lines anymore. We're going to use some wedged lines and some dashed lines over here. So wedge lines and dashed lines. And so if you're using a dashed line like this one over here, that represents a bond going away from you into the screen. But if you're using a wedged line over here, that represents a bond coming out of the screen towards you, almost like you're seeing a 3D movie. And then this is something that's on the screen, that's on the plane of the screen or the paper or whatever you're drawing it onto. So if I were to draw this in a 3D way using VSEPR theory, I would make one of the H's go essentially away from me. So that's going into the paper, into the screen. One of the H's with a wedge line would come out towards me as if it's going to poke me in the eye. And then the other H's would be just on the plane of the paper or the screen or whatever surface you're drawing on. So this is pointing up at you like it's going to poke you in the eye, and this is going behind you as if it's going behind your piece of paper. this one over here. So this is behind, and this is coming to the front. And these ones here are sort of flat on the paper in the plane. And that's how you would represent the 3D molecule once you know its shape using VSEPR theory or its geometry. So let's just go take a look at some visuals in your notes. You have a lot of visuals that you can use to learn VSEPR theory, and because it is a visual lesson, you do need to come and see some of these images. So here we have our Lewis structure for methane that we just saw, and we are going to see that molecules are actually three-dimensional, so they look more like this. And so you can see some bonds might come towards you, away from you, depending on how you rotate the molecule, but there's ways to represent that. So again, VSEPR is a way to predict molecular geometry, in other words, the 3D shape of a molecule. They don't always have to be drawn flat like this. This would be a Lewis structure, but we can represent them in their more 3D shape like this over here using VSEPR theory and using different drawings. So again, how do we go from this two-dimensional structure to this 4D shape over here? We have to use VSEPR theory. Before we go on to see some more details of VSEPR theory, we need to take a look at some terminology, just some background terms so that you understand what we're speaking about when we refer to VSEPR theory. So when we talk about molecular shape, that's how the atoms are arranged around the central atom and what shape they make overall in a 3D structure. And what's very cool is that you can actually measure angles between bonds. So you can measure the angles that forms over here, for example, between the atoms over here and here around the central atom. So this is a 120-degree bond angle. So that's what we call a bond angle. It's the angle formed between the nuclei of two atoms that surround the central atom of a molecule, and that's determined by the electron arrangements. Now, an electron arrangement, that's the way electrons arrange themselves around the molecule, around the central atom. And so we'll see different electron arrangements as well. But essentially, in VSEPR, using VSEPR, we're able to figure out a molecular shape, which is our 3D molecular geometry. And because things are 3D, there are bond angles. So you can actually measure angles between atoms around the central atom. So here we can see the bond angle between this and this around the central atom is 180 degrees. Here we have 120 degrees. Here in the tetrahedral shape, the bond angle is 109.5 degrees all the way around. Here in this trigonal bipyramidal shape, we have 90 degrees for these ones over here, and then 120 degrees for these ones here. And then in the octahedral shape, we have essentially 90 degrees all the way around. And these bond angles essentially are such that it minimizes the overall repulsion that the electrons have on each other. So that's what VSEPR is all about. It's about reducing the repulsion that's felt by the electrons, by the negative charges of the electrons. So we want to minimize those repulsions because that's a lower energy shape. And so what electrons are repelling each other? Well, within a molecule, you have different electron groups, we call it. You might have what's called lone pairs, right? That you have electrons in your lone pairs. You also have electrons within your bonded pairs over here. So this is electrons within bonds. And so you have repulsion that can happen between the electrons that are in bonds. You have repulsion that can happen between the electrons that are lone pairs. And you have repulsion that can happen between lone pair and bonded electrons. So it's happening everywhere, but they're not all equal repulsion. Generally, the strongest repelling that you'll feel is a lone pair repelling. So that's going to have a big effect on the overall shape of the molecule. After that, it's the lone pair bond repelling. And then the weakest repelling that happens is bond pair repelling. But either way, these are all going to play a role in repelling and leading to the overall final shape of the molecule that you're dealing with. But it's important to understand where VSEPR comes from, and it comes from this idea that the electrons, whether they're in pairs or whether they're lone pairs or whether they're in bonded pairs, will repel each other to different degrees. So we can see this over here. We have a central atom, and we have some electrons in bonds over here, and they're experiencing some repelling, and that's what's causing them to spread out into the shape that they're creating. So if we look at this molecule over here, methane, I mentioned before, some people might think, well, methane, the best way to draw it is this flat shape over here. with these 90-degree angles over here between the atoms. But if you do that, there's actually too much repelling that happens. And because there's too much repelling that happens, it's not the most stable structure. So the best angle to actually have for something like CH4 is where you have bond angles of 109.5 degrees. There, the atoms and the electrons have spaced out enough so that the repelling is minimal. And this is a more stable structure, and this is actually the shape that is experimentally supported for something like methane. So when we use VSEPR theory, we are using the concept of electron repelling to various degrees. And to learn how to use it, we have to learn the different symbols that we see in VSEPR tables to predict what the shapes are. That'll be our next video, figuring out what the symbols mean and then how to use tables to figure out what the shapes are. In this video, our main goal was really to go over what VSEPR is overall and the fact that we can use it to figure out molecular shapes of molecules because they're actually 3D. Before you go further, you should make sure you review your Lewis structures and that you know how to draw them. So if you don't know how to draw them and if you need to review terms, you can come back to the visual that's included in your VSEPR lessons. So here you can review how to do Lewis structures for elements and ions. You can review terms such as bonded pair, so electrons found within a bond, they're shared. Lone pairs, the electrons that are not in a bond, so they're not shared. So you should know those terms since they're involved in VSEPR. You should review the steps to drawing Lewis structures and also the exceptions like the incomplete octet, the expanded octet, what resonance structures mean. And once you have all that terminology understood, then you'll be in a better position to actually do VSEPR lessons. So one of the worksheets that you'll see in your supplementary visuals is just a little note on some background information you might need for VSEPR theory. After you go through the visuals that I just showed you on the previous screens, you'll be able to complete this. And we can complete some of this together before we end the video and jump into the next one. So a few things that you do need to be aware of is how to draw Lewis structures before you go into VSEPR. And that's for both elements and compounds. So you can take a look at the visuals to assist you with that. And then you need to review some terms like bonded pairs. So electron pair shared in a bond. And then you should also review things like your single bond, double bond, and triple bond. And term lone pair, which are electron pairs not involved in a bond. So if we have this over here, for example, this is ammonia. We'll call the bonded pair A. So these are some bonded pairs here. And then we'll call the lone pair B. So this is a lone pair over here. And you should be able to explain the difference between those two. And you should also review some VSEPR terminology that we saw in this video. First of all, what does VSEPR stand for? What's the whole point of it? What determines a shape? In other words, the electron repulsions determine shape, and we want to have a shape that will minimize the overall repelling of the negative charges of the electrons. That's our lower energy shape. And there's different degrees and types of repelling that you'll see with the different types of electron groups. So the different types of electron groups are essentially your lone pairs and also your bonded pairs. And we found that the strongest repelling is between lone pair and lone pair. So if you have lone pair repelling, that's the strongest repelling that happens. The weakest repelling is between bonded pair and bonded pair. And then sort of the intermediate in between is lone pair, bonded pair repelling. But either way, they will all lead to repelling, which leads to our overall shape of the molecule. And so, again, all this information is simply coming from your visuals that you see over here. So we just review these terms using the visuals, and you can go and fill in some blanks there overall to figure out what the overall shape of the molecule is. So we're going to go and take a look at the terms bond angle and just fill in some blanks there. So let's go ahead and do that. So when we look at the molecular shape overall, that's going to depend on a couple things: the length of your bond, but also the bond angle. And so you can actually have angles between the atoms in a molecule around the central atom. So that's going to determine the overall molecular shape. And the molecular shape is really the relative position of atoms in a molecule around a central atom generally. And so you can have a bond angle, which, like I said, is the angle formed between two nuclei, the nuclei of two atoms that surround the central atom. And those bond angles are determined by simply our electron arrangements, which are the way that the electron groups arrange themselves around the atom due to the repelling. Again, the VSEPR theory uses the electron arrangements to predict bond angles and molecular shape. So overall, to summarize, VSEPR theory will look at the repelling that happens between different electron groups like lone pair, lone pair, lone pair, bonded pair, bonded pair, bonded pair. And those electron groups essentially just arrange themselves in such a way that will that arrange themselves due to the repelling of the electrons having the same charge. And so we can use the different types of repelling that will happen to predict how the atoms will arrange themselves to minimize that repelling. And that will lead us to our 3D shape overall. So when we look at what effect do lone pairs have on bond angles, well, we can take a look at a picture here. So if we go take a look at a lone pair, let's find the picture with a lone pair here. Let's go to this picture here. So here we don't have any lone pairs, but here we have a lone pair, and here we have two lone pairs. So take a look at what happens as you add lone pairs to a molecule. So if we replace the bonded pair here, take away this atom, put a lone pair instead, we get this angle. If we replace two atoms instead by two lone pairs, then we get this angle over here. So as you can see, there's a clear trend happening when we add lone pairs, and we're just increasing the amount of repelling that's happening. And so as a result, if you're increasing more repelling here and here, you're decreasing the bond angle between these two atoms that you have over here. So really, with more repelling, we're leading to a decrease in the bond angles overall. So let's go ahead and write that in there, and you can do a drawing to explain that, but essentially it decreases bond angles because we have more repelling squeezing the atoms together. And so it's a good idea for you to go through these visuals so you can get a better idea as to how we use those electron arrangements to predict the overall 3D shape. The other thing we saw as well that's important to go through in the visuals are the wedge dash drawings. Become familiar with the wedge meaning coming towards you, the dashed line going away from you, and these solid lines mean on the plane of the paper. So become familiar with that, because when we do VSEPR shapes, we're going to have to represent them using their 3D drawings overall. So in the next video, we're going to take a look at the shapes in more detail and how to use some tables to predict what the actual molecular geometries are.